In the previous lecture, we have discussed in very detail a very important theorem which is called Bloch's theorem. And you have seen that Bloch's theorem actually gives a technique to write down the wave function of an electron moving in a periodically varying potential field. Okay? And now we are going to see a very important illustration using this Bloch theorem, or you can say that now we will see the application of this Bloch theorem. Actually, the most important and most simplest application of Bloch theorem is found in a model which is known as Kronig-Penney model, and popularly it is called KP model. Okay, so you can say that this KP model is the simplest example of one-dimensional periodic potential, and this has been treated by Kronig and Penney, and this potential is shown in this figure. How this potential varies is shown in this figure, and we will discuss it actually. In fact, this KP model illustrates all the essential features of the behaviors of electrons in a periodic potential. Okay. In fact, as you can see in this figure that the potential or the potential energy of an electron in a linear array of positive nuclei is assumed to have the form of a periodic array of square wells. Here, this region between -b and 0, okay, and A plus B, this is actually the potential well, okay, and A plus B is the period of the potential. It means you can say that V of x is equal to V of x plus A plus B. So A plus B is the period, because you can see the potential at x equal to 0 is equal to V naught, and at x equal to A plus B again it is V naught. So the potential repeats its value after an interval of A plus B. So you can say that A plus B is the period of this potential. Okay. Actually, at the bottom of the potential well, that is in this region, you can see that it means we are talking about a region for which this 0 is less than x and this is less than A. This is actually the bottom of the potential. Okay. Actually, in this region, the electron is assumed to be in the neighborhood of a nucleus, and the potential energy is taken to be 0. Whereas outside of the well, that is, you can say that this minus B is less or equal to sorry, here actually I have marked it in a wrong manner. Let us see. Okay. In fact, you have to take here 0, here minus B. Okay. And so this has been also written wrongly. Okay. This is in fact B. Here x is equal to A. Here it will be A plus B, and here this this is in fact A, this is B, this is again A, and this is B. And so here it will be 2A plus B, and this will be 2 times A plus B. Okay. So you can see the potential at this x equal to 0 is just equal to 0. Okay. and at this x equal to a plus b is again it is 0. So a plus b is the period of this potential. Okay, or in other words you can also say that at x equal to minus b the potential is v naught. Okay, and again at this point potential is equal to v naught. So a plus b is the period of the potential. So as I have told you that at the bottom of a well, when you say bottom of a well, what does it mean? This is your potential well, and in this region you can see 0 is less than x and this is less than a. This is the region of the potential well. Okay. In fact, in this region the electron is assumed to be in the vicinity of the nucleus, or you can say the atom, and the potential energy here is equal to 0. Okay, at the bottom of the potential. Okay, but outside of this potential well, when you say outside of the potential well, this is the region which is outside of the potential well, and for this region you can say this minus b is less than x and this is less than 0. In this region actually potential is constant and this is equal to v naught. Okay, although this model implies a very crude approximation to the type of periodic potential existing inside the lattice. Why we say that this is a crude approximation? Because you can see that in this figure you can see that the potential falls abruptly to 0 from v naught to 0. But an abrupt fall of potential is not a physical fact, it's not a physical reality. So you can say that this is an approximate potential, although it is a crude approximation of periodic potential existing inside the nucleus, inside the lattice. But it is very useful to illustrate the various important features of the quantum behavior of electrons in the periodic lattice. And so in theoretical calculation, we invariably use this type of periodic potential. Okay. Now, as you have seen that Bloch's theorem gives a method, gives a technique to write down the wave function for an electron, or the solution of Schrodinger equation for an electron moving in a periodically varying potential. Okay, and from that result we can get the idea of the quantum behavior of electron, and from which we get actually the idea of energy bands in the solid. So first of all, as here there are two regions. The first region is 0 less than x less than a, and the another region is minus b less than x less than 0. For these two regions we will set up the Schrodinger time independent equation for an electron, and then we will try to solve those equations with the help of Bloch's theorem. And after solution you will get very interesting result to deal with the proper problem of band theory of solids. Okay. So let us see how the potential varies. As I have told you that you can see that this v of x is equal to 0 in this region, that is 0 less than x less than a. This is the region where potential is 0. Okay, and this v is equal to v naught in the region minus b less than x less than 0. So you can say that this is your first region, this is your second region. Now we will write down the Schrodinger equation in these two regions. Okay, actually here each of the potential well is a rough approximation for the potential in the vicinity of the atom or nucleus, as I have told you earlier. Okay, so for first region you can see the potential function is 0. So Schrodinger equation in the first region defined by these limits will be what? this will be d2 psi 1 by dx square plus 2m over h bar square E psi 1 equal to 0. Actually, in Schrodinger equation, you know there is E minus V, but since V is 0 in this region, as you can see here, so the equation is like this, okay? And this equation can be equivalently written as d2 psi 1 by dx square plus alpha square psi 1 equal to 0. Here, alpha is equal to a square root of 2me over h bar square. This is a positive constant, okay? And so, psi 1 is the wave function of the electron in this first region where potential is 0, that is inside the potential well. But outside of the potential well, that is in the region minus b less than x less than 0, you know, potential is not 0, it is V naught. And so, the Schrodinger equation will be written as d2 psi 2 by dx square plus 2m over h bar square E minus V naught psi 2 equal to 0, okay? But here we will assume that the energy of the electron is less than this potential V naught. Actually, under this assumption, our electron will be bonded inside a potential well, and so we assume that the total energy of electron is less than the height of this potential barrier V naught. And so in that condition, this E minus V naught will be a negative quantity. And so you can write this Schrodinger equation in this manner. This is d2 psi 2 by dx square minus 2m over h bar square V naught minus E psi 2 equal to 0. And we take this 2m over h bar square times V naught minus E equal to beta square. So you can write this equation is d2 psi 2 by dx square minus beta square psi 2 equal to 0, where beta we have assumed is equal to a square root of 2m times V naught minus E over h bar square. So you can see here beta is also a positive constant, but it depends on the value of the energy of electron E. Alpha and beta both are functions of E, okay? Now, see the form of this equation 1. This is just the equation of a simple harmonic motion. So you can think that the solution of this equation 1, that is psi 1, must be of oscillatory nature. You will think it. So on this basis, you can write the solution of that Schrodinger equation in this manner: psi 1 x equal to a times e to the power alpha x plus b times e to the power minus alpha x, okay? And see the equation number 2. Here there is not plus sign but minus sign, and you know in this form of differential equation, the solution is exponentially varying, okay? And so solution of this equation 2 is well known, and that can be given as psi 2 of x equal to c e to the power beta x plus d e to the power minus beta x. Actually, in these two equations, we have used 4 arbitrary constants, a, b, c and d. These are arbitrary constants or integration constants. Since these equations are differential equations of second order, so for solving this equation in a proper manner, you must have to integrate 2 times. And if you will do integration 2 times, definitely there will be 2 integration constants. And those integration constants are actually a, b, c and d. And these constants you will see later on that can be evaluated by use of the proper boundary condition, okay? Till now, we have written the Schrodinger equation and have also write down the solution of those equations, only observing the form of the differential equation. But what about the actual situation? Here, the potential under which our electron is moving is not a constant potential, but it is a periodically varying potential. Not only varying, but periodically varying. And you have learnt in Bloch's theorem that if a particle moves in a periodically varying potential, then the solution of Schrodinger equation is a plane wave multiplied by or modulated by a function uk of x. So, taking this fact of Bloch's theorem under account, in present situation, you can say that the solution of the first Schrodinger equation, that is psi1 of x, this can be written as u1 of x times e to the power ikx. This has been written on the basis of Bloch's theorem. Okay? Definitely, you have already studied Bloch's theorem, so there will be no problem in understanding this. And in the similar manner, you can write the solution of the second equation in terms of the Bloch function, and that will be psi2 of x equal to u2 of x times e to the power ikx. Okay? Now you can see from these two equations we can easily obtain expression for u1 of x and this u2 of x. You can see u1 of x will be what? This will be psi1 of x over e to the power ikx. But psi1 of x we have defined in this equation 1a, and this is a plus e to the power I alpha x plus b times e to the power minus I alpha x and over e to the power ikx. So now divide each term of the numerator by this factor e to the power ikx, and after dividing you will get that u1 of x is equal to a times e to the power I alpha minus k times x plus b times e to the power minus I alpha plus k times x. Okay? This is very simple calculation. And in the similar manner, see here, u2 of x will be equal to psi2 of x over e to the power ikx. But you can see psi2 of x we have defined in this equation 2b. So let us substitute the value of psi2 of x here. This is c e to the power beta x plus d e to the power minus beta x and over e to the power ikx. And so after division you will get that e2 of x is equal to c e to the power beta minus ik times x plus d e to the power minus beta plus ik times x. Okay? And as I have told you earlier that the arbitrary constants a, b, c and d existing in these equations can be obtained by or can be eliminated by using the proper boundary conditions. You know, the wave function actually satisfies the proper boundary condition, that wave functions are continuous and at a boundary, and its first order derivative are also continuous. Okay? So you can say that psi and its derivative d psi by dx will be continuous at the boundaries. Now since psi and d psi by dx are continuous, so you can say that this implies u and du by dx will be also continuous at the boundaries. Okay? So what will be the boundary conditions? You can see there are actually two boundaries here. You can see this x equal to 0. This is one of the boundary. Okay? X equal to 0 is one of the boundary. And so at x equal to 0, psi1 of x will be equal to psi2 of x, and so that u1 of x will be equal to u2 of x at x equal to 0. And also their derivatives will be equal at this boundary. So you can see I have written here the boundary conditions, that u1 of 0 is equal to u2 of 0. When you write u1 of 0 is equal to u2 of 0, what does it mean? It means the value of u1 at x equal to 0 and the value of u2 at x equal to 0 are equal. Okay. Again, the first order derivative is also continuous, so you can write that du1 by dx at x equal to 0 and du2 by dx at x equal to 0 both are equal. Okay. Now, again you can see the period of this potential is A plus B. So, this A and minus B are same point. A and minus B are same point because the potential A repeats itself. When you can see just before minus x equal to minus B potential is 0. Okay, and just before this x equal to A potential is 0, and at minus x equal to minus B potential abruptly rises to V0, and at x equal to A again you can see the potential abruptly rises to V0. So you can say that A and minus B are the same boundary. Okay, so the value of potential at x equal to A and at x equal to minus B are same. And that's why you can say that our wave function u1 at x equal to A and u2 at x equal to minus B will be equal. This is your third boundary condition. And in a similar manner, since the first order derivative of a wave function is also continuous, so you can say that du1 by dx at x equal to A and du2 by dx at x equal to minus B will be also equal. So these are the four boundary conditions. Since we have to evaluate or eliminate four arbitrary constant A, B, C, D, so we must need at least four boundary conditions. Okay, so using all these four boundary conditions we can eliminate or we can evaluate the values of A, B, C and D. Okay, now let us apply this first boundary condition 5A, okay, which says that u1 is equal to u2 at the boundary x equal to 0. This condition we will now apply on equation 3 and 4. See equation 3 and 4. This is your equation 3 and this is your equation 4. According to that boundary condition, this u1 of x and u2 of x will be equal if x is equal to 0. So now let us find the value of u1 at x equal to 0. You can see when you will substitute x equal to 0 in the RHS, then there will be e to the power 0 factor in both of the terms in RHS, and that is equal to 1. So u1 at x equal to 0, this will be simply A plus B. Okay. And in the similar manner, you can also see that u2 at x equal to 0 will be what? That will be equal to C plus D. But according to the boundary condition, u1 at x equal to 0 and u2 at x equal to 0 are equal. So we can say that A plus B is equal to C plus D. Okay. Now, for applying the boundary condition 5B or 5D, first of all we will have to find the first order derivative of u1 and u2 with respect to x. So let us first of all find du1 by dx. See the expression here. u1 of x, this is equal to this much, you can see. And we will differentiate it. This is a very simple differentiation, so you can see I have written here and you can check it. So du1 by dx will be equal to I times alpha minus k times A times e to the power I alpha minus k times x, and minus I times alpha plus kb times e to the power minus I alpha plus kx. Okay. This is du1 by dx. In the similar manner, you can find du2 by dx from this equation 4. So differentiate equation 4 with respect to x and you will get du2 by dx equal to beta minus ik c e to the power beta minus ik times x and minus beta plus ik times d e to the power minus beta minus ik times x. Okay. So these are the values of the first order derivative of u1 and u2. Now you can apply this boundary condition 5b. When you will take x equal to 0, then du1 by dx and du2 by dx will be equal. And taking x equal to 0, all the exponential factors in the RHS of these two equations will be 1. Okay. And so we can write this condition in this manner: I times alpha minus k times a minus I times alpha plus k times b, and that is equal to beta minus ik times c minus beta plus ik times d. So this result has been obtained by applying the second boundary condition. Okay. Now apply the boundary condition defined in this equation 5c on equation 3 and 4. You can see this boundary condition says u1 at x equal to a and u2 at x equal to minus b are equal. So let us put x equal to a in the RHS of equation 3 and x equal to minus b in the RHS of this equation 4. And after substituting these, you will get that u1 is equal to u2 and your result will be a times e to the power I alpha minus k times a plus b times e to the power minus I alpha plus k times a, and that is equal to c e to the power minus beta minus ik times b and plus d e to the power beta plus ik times b. Okay. So this result has been obtained by applying this third boundary condition on the above two equations. Okay. Now finally we will apply this boundary condition 5d. See here. And for this, what we will do? You have to put x equal to a in this equation, in the RHS of this equation 7, and x equal to minus b in the RHS of equation 8, and then we will equate those two values. So doing this, your result will be what? You can check it. After that, we will get I times alpha minus k e to the power I times alpha minus k a minus I times alpha plus k times b e to the power minus I alpha plus k into a, and that will be equal to beta minus ik times c e to the power b minus beta minus ik times b and minus beta plus ik times d e to the power beta plus ik b. Okay. So in this way, applying the four boundary conditions, now we get four equations which are defined from equation, see here, equation 6 in 6a, in equation 6b, in 6c and 6d. Actually all these are actually the simultaneous equation, and you know from the theory of determinant that these equations will have non-zero solution, non-vanishing solution, or you can say that A, B, C, D will be non-zero only when the determinant of the coefficients or multiple of A, B, C, D will vanish, will be zero. So now let us make a determinant of the coefficients of A, B, C, D in these four equations. So you can see In equation 6a, the coefficients of a, b, c, d, all a is equal to 1. Here there will be 1, here is 1, here is 1. Okay. Now, in this equation 6b, coefficient of a is what? This is I times alpha minus k. Coefficient of b is minus I times alpha plus k. Okay. Minus sigma. And for writing this in determinant form, you have to bring these two terms in LHS. So when you will bring it in LHS, then the positive term will become negative and the negative term will become positive. Okay. So let us see. In this condition, in this equation, the coefficient of A is e to the power I times alpha minus Ka, and coefficient of B is e to the power minus I alpha plus K into A, and the coefficient of C, this will be e to the power minus beta I K times B, and that of D will be e to the power beta plus I K times B. Okay. And in the similar manner, here you can see the coefficient of what are the coefficients of A, B, C, and D. So, according to the theory of this simultaneous linear equation, you can say that this determinant, actually whose elements are simply the coefficients of A and B in above 4 equations. Okay. I am not giving a reading, you can check it and you can write down these things in your notebook, and this determinant should be equal to 0. Okay. Actually, this is a very complicated determinant, but when this determinant is solved, we get a very simple result. Actually, the algebra of solving this determinant have been not done by me here. And I will also suggest you can try its solution separately, but never try its solution in your examination. In examination, you must remember the solution of this determinant. You should remember it. You should write down it directly, because the solution will be very lengthy and it will take time, but no reward will be given to you, because we are dealing the physics, not the mathematics. Okay. So remember, when this particular determinant is solved, we get a very interesting result which is given like this. This is beta square minus alpha square over 2 alpha beta times sine hyperbolic beta b times sine alpha a plus cos hyperbolic beta b times cos alpha a, and that equal to cos k a plus b. Okay. So this is the solution. This result is obtained after the solution of this very determinant, and as I have told you, you must remember it. Okay. But how this result can be simplified, or what information we get from this result, and actually this is done. This problem was solved by Kronig-Penney by considering a particular assumption. If anyone will try to obtain the interesting results from this, or deal with the behavior of electron in the crystal by this original result, the discussion will be very complicated. So, to simplify this equation, actually Kronig-Penney considered the case when V naught tends to infinity. Mark it. This has been considered by Kronig-Penney, that V naught tends to infinity and B tends to 0. So you can see, when you say that V naught tends to infinity, it means you are talking about a potential barrier whose height is very large. V naught is tending towards infinity, but its width is very small. This will be very small. But in such a manner that V naught B, which represents the area of this area under this curve, that remains finite. But you know from the definition of Dirac delta function that Dirac delta function delta x is infinity at x equal to 0 and it is 0 otherwise, okay, otherwise. But the area under this delta function, which is given by this integral delta x dx from minus infinity to plus infinity, is always equal to 1 and that remains constant. Okay. So this property which actually Kronig-Penney has applied for simple solution of this equation, that V naught tends to infinity and B tends to 0, but V naught into B remains finite. This property actually implies that this potential barrier becomes Dirac delta function. Okay? So in this situation we can treat this potential barrier as a Dirac delta function. Okay? And under this condition, there is a finite probability of electron with energy E less than V naught to tunnel from one cell to next. As you can see, we have assumed that the energy of the electron E is less than V naught. If you consider that this is the energy of our electron, which is less than V naught, but when you will consider that this potential, the width of this potential barrier is almost 0, then there will be a finite probability of electron from moving from one cell to another even when E is less than V naught. Okay? And so there will be a propagation of electron from one region to another. Okay? Okay. And under these circumstances, the model is modified to one of the series of wells separated by infinitely thin potential barriers. Okay? So, in fact, in this condition, what will be now our this equation 10, which is the original solution of this determinant? You can see. In this limiting condition, we have assumed that V naught tends to infinity and B tends to 0. Okay? And V naught B in fact is called barrier strength, which represents actually the area. Okay? But what will be the values of different terms in this equation 10 under this limiting condition? Again, see this limiting condition. V naught is tending towards infinity, B is tending towards 0, but V naught B is constant, it is finite. Since B is tending towards 0, so sine hyperbolic beta B in this limiting condition will tend to simply beta B. You know, limit theta tends to 0, sine theta equal to theta. Similarly, limit theta tends to 0, sine hyperbolic theta equal to theta. And cos hyperbolic theta is equal to 1. So in this limiting condition, when B tends to 0, cos hyperbolic beta B will be equal to 1. And as you can see, this beta square minus alpha square will be almost equal to beta square. Why? You can see that we have assumed that this V naught is much greater than E, because you have assumed that this V naught is tending towards infinity. But beta is equal to root over 2m V naught minus E over h bar square. Sorry, here there is V naught minus E, 2m V naught minus E. But you can neglect this E in respect of V naught, because V naught is tending towards infinity. And alpha, you have seen, this is simply root over 2me over h bar square. But this V naught is much greater than E, so beta will be much greater than alpha. And so this alpha square can be neglected in comparison to beta square. So beta square minus alpha square is simply equal to beta square. Okay? And cos k times A plus B. Since B, you have seen, is tending towards 0, so taking B 0, this will be cos k. So the assumption which the Kronig and Penney has considered to solve that very equation, under that limiting condition, what will be now the form of this equation 10, you can see. Here alpha square will be neglected. Instead of sine hyperbolic beta, we will simply write beta b. And for cos hyperbolic beta b, we will write 1. And for cos k times A plus b, we will write simply cos ka. So making these substitutions in that equation 10, our result will become like this. This is beta square over 2 alpha beta times beta b times sin alpha a cos alpha a equal to cos ka. Okay. Now the first term we can write in a proper manner. You can see here there is no a in the numerator, but I have multiplied here by a. So this is written as beta square ab divided by 2. But here this beta and beta get cancels, and as we have multiplied by a in the numerator, so you must multiply it also in denominator. So there is alpha a, and cos alpha a equal to cos k. So in first term we have simply multiplied by a in both numerator and denominator and nothing else. Now this factor beta square into ab divided by 2, this is written as p. I have written p equal to beta square ab divided by 2. Okay. And so our result is p times sin alpha a by alpha a plus cos alpha a equal to cos k. This is the simple form of that equation which have been obtained after the solution of determinant. Now you can see beta square, you know this is 2m times v naught minus e over h bar square, okay, and times ab by 2. But as you have seen, since v naught is very large here, it tends towards infinity. So in this condition we can neglect this e, and this 2 and this 2 will cancel out, and your result is mv naught ab divided by h bar square. Okay. Actually, this P is the measure of the strength of the potential barrier. Okay. If value of P is large, it means electron is more tightly bonded inside the potential well. But if when P will be small, it means electron is loosely bonded or almost free. So the electron is strongly confined or strongly bonded to the potential well, or it is free. That is decided by the value of this parameter P. Okay. So I have mentioned it here. You can see that P is the measure of the area V naught B of the potential well. This thus increasing P has the physical meaning of binding an electron more tightly to a particular potential well. Okay. Now, what conclusion, what result we actually obtain from this result, you can see this figure. Here, actually in this figure, a graphical plot of P times sin alpha A by alpha A plus cos alpha A, which is actually the LHS of this equation A, okay, has been plotted in against of alpha A, okay, and for a particular value of P, this actually in this graphical plot P has been almost assumed to be 3 pi by 2, and for that this graph has been plotted. The graphical plot of this P sin alpha A by alpha A plus cos alpha A in against of alpha A is shown in this figure. And what informations we get from this figure you can easily see. Okay, you can see in RHS of this equation there is cos Ka, and you know the limiting value of cos Ka will be what? This cos Ka will lie between -1 and +1. It means -1 is the least value, minimum value of cos Ka, and +1 is its maximum value. Since RHS will be never less than -1, never greater than +1, so LHS should be also never less than -1 and never greater than +1. But what actually is seen in this graphical plot? You can see at this point alpha A equal to pi. After this, there is a slight deviation of the curve, and this curve is in a region where alpha A is less than -1. Okay? And on the other hand, after this 2 pi, you can see again that there is a deviation in the curve, which implies that for this deviation, this LHS will be greater than +1. But it is not possible physically. So definitely its physical meaning will be something different. Okay? So you can see that this is this result which we have actually obtained here. This is actually the condition which must be satisfied for solution of the wave equation to exist. And since cos Ka lies between -1 and +1, so the left hand side should assume only those values of alpha A for which its value lies between -1 and +1. Okay? And such values of alpha A are therefore represent the wave-like solution. Okay? And wave-like solution means the solution like Bloch function. Okay? But and if it is a wave-like solution, those values of alpha A will be allowed values. But as you can see that the other values of alpha A for which this cos alpha A is less than -1 and greater than +1, that can not be allowed, and the energy of the electron in that condition will be not the energy of electron in the crystal. Those electrons are not present in the crystal in that energy level. Okay? So in this figure you can see the shaded region which I have shown in this figure, those are actually the allowed energy band, because in the shaded region you can see here the value of this parameter mentioned on this y-axis is equal to 1, and here the value is -1, and those are allowed value. Okay? But the unshaded region, are the allowed region or allowed energy band, but in the region of unshaded region, cos alpha is, not cos alpha, but alpha A has a value for which cos alpha A is greater than 1 and less than -1, which is not possible. So this unshaded region represents the forbidden energy gap. Electron cannot have such an energy so that it will remain in that energy state. But the shaded region represents the allowed energy band. Actually, all these things I have mentioned it here. You can see that this equation A, which I have mentioned it here, this is the this is actually the required condition which must be satisfied for the solution of the wave equation to exist. And you can see, I have mentioned it here, that the RHS of equation must lie between +1 and -1. Therefore, a solution exists only for those values of E for which LHS is between these limits. In other words, there is a solution of the shaded region, okay, and no solution for outside it. Since alpha is related to E, this means that the electron may possess energy within certain bands but not outside of them. There are allowed shaded region and forbidden unshaded region bands. And this is the basic conclusion of this model. Actually, we will see in the next, this is actually the first part of the lecture on this KP model, but we will provide a second part of this lecture where we will discuss the important special cases from which you will see that all the quantum mechanical behavior of electron moving in a periodic potential can be discussed from this theory. Okay, thank you very much.